Eyebrows. If you're ever feeling down and want to pick me up, take a picture of somebody you don't like and remove their eyebrows. Guaranteed way to make yourself giggle at how ridiculous they look. Turns out our collective chuckle to a browless face is one of evolution's happy accidents. Your eyebrows serve a purpose on your face. The arch in hair direction divert sweat and rain away from your eyes while cutting glare and blocking dust. That's why hundreds of thousands of years of evolution took away most of our body hair, but somehow the eyebrows stayed. Then humans got intensely social, and eyebrows were assigned a second job they were never designed for. Studies show that removing eyebrows from a familiar face ruins recognition accuracy more than removing the eyes does. Your brain uses them as an anchor for identity in a way it doesn't even fully register consciously. On top of that, a single eyebrow raise carries emotional data: surprise, skepticism, a warning that would take several words to say out loud. Apparently, humans got so attached to eyebrows that we started breeding dogs to have expressive brows too. We love eyebrows so much we started installing them on other species. None of this was the plan. Eyebrows were just good protective hair that stuck around, and it's now doing more social work than you thought possible. Fingerprints. If you touch your phone as much as the average adult, there's a very good chance you're leaving smudges all over the screen with your fingerprints. Next thing you know, your fingerprints are taken from your phone to be used against you in court. But the real reason those ridges exist actually has nothing to do with forensics or solving crime. The leading explanation is that fingerprint ridges regulate moisture. The ridge and furrow architecture manages the thin film of water that builds up between your skin and a surface, channeling and evaporating to keep friction stable across wet and dry conditions. Without that regulation, your grip on smooth surfaces in anything other than perfect dry conditions becomes unreliable when you're handling something small, sharp, or important enough not to drop. The tactile side is just as useful. The ridges sit directly over dense clusters of sensory receptors, and the physical patterning amplifies the spatial detail your nervous system picks up from surfaces, letting you read texture, detect slip, and manipulate small objects with a precision that a smooth fingertip simply couldn't match. None of this was intentional. Fingerprint ridges are a patterning outcome of how skin develops, the same way sand forms ripples under moving water. The epidermis folds under mechanical stress during fetal development. Evolution then exploited the friction and sensory benefits that came with it. The forensics industry built an entire global infrastructure on a grip optimization that your fingers grew by accident. Lips. Imagine explaining kissing to an alien. You press the most sensitive part of your face against another person's face. Sometimes you do it to say hello, sometimes goodbye, occasionally to a relative you'd rather not. It makes no evolutionary sense on the surface, and that's exactly what makes lips interesting. Lips are densely packed with sensory receptors, more than almost anywhere else on your body, making them exceptional at detecting temperature, texture, and pressure. That sensitivity originally served feeding, sealing around food, managing what stays in your mouth, and in infants, creating the suction needed for nursing. Muscle control came along with that, and once language evolved, it turned out precise lip movement was exactly what you needed to produce half the sounds in human speech. There's also the social layer aspect. Lip shapes broadcast mood faster than words: a pressed smile, a pulled frown, a single pursed lip of skepticism. In large groups where reading people quickly matters, that's genuinely useful signal bandwidth. As for kissing, current thinking treats it as an exaptation, an old behavior repurposed for something new. Mouth-to-mouth contact appears in ape social grooming, and somewhere along the way, humans seem to have redirected it toward bonding. The science is still interpretive, which is a very polite way of saying nobody fully knows why we do it. Evolution handed us feeding equipment. We built a communication system, a social ritual, and something that sells Valentine's Day cards. White sclera. Look at your roommate's eyes, and then your dog's. While your dog probably stared back at you lovingly, and your roommate is now suspicious of you, that's not the biggest difference. Turns out the sclera, the white part of the eye, are way more visible in humans when compared to other animals. The white is essentially a coordination tool that evolution stumbled into, because your sclera is bright white and contrasts so sharply against your iris and pupil, anyone near you can read exactly where you're looking from across a room without you moving your head, making a sound, or doing anything at all. The wiring is so strong that human infants follow eye direction instinctively. The color of your sclera can also signal underlying health conditions. The most common is bloodshot eyes that could mean irritation, allergies, or even broken blood vessels. And if the entire sclera turns yellow, it's often a sign of jaundice that could mean trouble in your pancreas, liver, or gallbladder. And even more rare is blue sclera, which could mean a serious genetic bone condition. A non-white sclera isn't a reason to have a full-blown panic attack, but it's definitely a sign to check back in with your doctor. What's interesting is that this probably wasn't a top-down redesign. The leading explanation is that as human faces changed to become flatter and more forward-facing, more sclera became exposed, got depigmented, and the high-contrast look came along as a package deal. Other species can read human gaze in experiments too, which suggests the contrast is just good visual engineering wherever it came from. Your eyes have been broadcasting your attention to everyone around you your entire life, including your dog, who figured out where you hid the treats. Achilles tendon. If you're a fan of the NBA, you've seen a growing trend of players tearing their Achilles at the worst moments. It's painful, the recovery is long, and it's ruining the playoffs. Why must this little tendon named after Brad Pitt be so important for the human body? The Achilles tendon connects your calf muscles to your heel, and its main trick is storing energy. Every time your foot hits the ground, the tendon stretches like a spring and then releases that energy back into your next stride. Research suggests tendons can return the vast majority of that stored energy, which means a significant portion of the work in every step isn't coming from your muscles firing, it's coming back from the ground. Chimps and gorillas have short Achilles tendons and long calf muscle fibers, which suits climbing, but makes this energy return far less efficient. Humans flip that ratio, and the compounding effect across millions of steps is enormous. There's a less obvious benefit too. Because the tendon is long, the calf muscle doesn't need to be as big or reach as far down the leg, keeping the lower leg lighter. Imagine having calves twice the size. That would make every step so much heavier and every jump twice as hard. If you're a bodybuilder, that's a great trade-off, but if you play any athletic sport, that's a terrible deal. The cost of tuning a tendon this tightly for elastic performance is that it becomes vulnerable in ways a less optimized system wouldn't be. Your Achilles is extraordinarily strong and surprisingly fragile at the same time, which is a very specific kind of engineering problem that elite athletes discover at the worst possible moment. Large glutes. If you're into TikTok workouts, you've seen over 50 different glute activation exercises on social media that'll take you a full day to get through in the gym. While fitness influencers are notoriously scam artists, this one bit of advice is actually real. The reason your glutes need activating at all is one of the stranger details in human anatomy. Your gluteus maximus is remarkably quiet when you walk. Studies that measure muscle electrical activity show it barely fires during normal walking, which makes it seem like an overbuilt muscle for a species that mostly gets around on foot. But the moment you start running, it lights up completely. It stabilizes your trunk every time your foot hits the ground, decelerates your swing leg just before each stride, and keeps your body from folding forward under its own momentum. Without it, running at any real pace ends in a spectacular faceplant. Bipedal posture is what built the large gluteus maximus in the first place. Walking upright on two legs reorganized the entire hip architecture, and a powerful hip extensor came along with that. Running, which became a part of the human ecological toolkit later, essentially inherited a muscle that turned out to be exactly what it needed. Even though other apes can run, none of them are built for it the way humans are. That's all thanks to your spectacular butt. Chin. If you've been staring at your chin, wondering if you should be look-smaxing and bone-smashing, please don't. Turns out this bony ledge jutting off your front jaw is so uniquely human that paleontologists use it to identify Homo sapiens in the fossil record. Not even our closest extinct cousins, the Neanderthals, had chins. The truth is, your chin holds your face together in ways you've never noticed. That forward projection creates the structural platform for the mentalis, the muscle responsible for your lower lip and the skin of your chin moving at all. Every pout, every skeptical lip press, every "I'm trying not to cry" face runs through it. Without the chin's geometry, we might all have that dreaded Botox face with unmoving lips. Some research also suggests the chin's projection helps manage mechanical stress for the jaw during biting. And then there's attraction, which scientists have floated as a possible explanation for why chin shapes vary so much across human populations. Seems like chin attractiveness has gotten way more popular among young men recently. The real twist is that the chin probably wasn't selected for any of this directly. Current analysis points to it showing up as a spandrel. That's just a fancy word for an evolution side effect. Over hundreds of thousands of years, the human face got flatter, and the skull reorganized itself. And voila, that's how your chin formed. The chin basically showed up uninvited and found multiple jobs. Not bad for an architectural accident. Thick foot skin. If you've personally attacked your feet with one of those cheese grater foot files, this section is going to feel a little awkward. That rough, hardened skin you've been scraping off is doing something cushioned shoes still haven't managed to replicate. Research on people who have never worn shoes finds that thicker, harder calluses don't reduce tactile sensitivity the way a cushioned sole does. The foot stays protected from abrasion and rough surfaces while maintaining the sensory feedback needed to detect slip risk and adjust to uneven ground. Cushioned shoes trade that feedback away for comfort, which turns out to be a more complicated swap than the shoe industry would prefer you to think about. The callus also self-maintains, thickening exactly where stress is highest and repairing as it wears without requiring a receipt or a replacement cycle. It's a dynamic, location-specific, self-updating protective layer that your body builds and manages automatically. In reality, calluses aren't an evolutionary design, they're a mechanical response. Skin doing what skin does under repeated pressure. The surprise is that this simple, dumb process produces something more functionally sophisticated than decades of footwear engineering. Your body didn't set out to build the perfect shoe, it just responded to the ground, and the ground taught it everything it needed to know. Next time when you see someone walking without shoes, don't dismiss them as hippies just yet. They might be designing the next generation of footwear. Kneecap. If you sit down with your legs straight and move the top of your knee in all directions, that's your kneecap. And don't worry, your knees aren't falling off. Moving the kneecap around is perfectly normal. Your kneecap is the only bone in your body you can grab and wiggle around with your fingers. The kneecap, or patella, works by sitting in front of the knee joint embedded in tendon, which shifts the pull angle of your quad muscles and gives them more leverage when straightening your leg. The practical result is that your muscles do the same amount of work while using less force across every squat, every step uphill, every time you stand up from a chair without using your hands, feeling proud of yourself. It's also absorbing the friction that would otherwise grind directly through the tendon. The strange part is that the kneecap wasn't engineered by evolution, it simply grew. Bones like the patella form by hardening inside tendons wherever mechanical stress is highest, which means your body essentially identified a load problem and quietly calcified a solution into place. The sophistication is a side effect of a remarkably simple process. Put enough pressure on soft tissue for long enough, and bone shows up. Turns out, the loose-feeling thing sliding around your knee is the reason you can stand up at all. Tooth enamel. If your dentist has ever told you your enamel is wearing down, causing that sudden painful tinge when you bite down on your favorite ice cream, enamel might feel like an evolution glitch. Enamel is the hard outer layer of your teeth, and thickness matters in two ways that aren't the same thing. The obvious one is resisting fracture. Thicker enamel is better at handling the mechanical stress of crunching, chewing, and processing food without the tooth breaking. The less obvious one is wear tolerance over time. A thick enamel layer means teeth stay functionally shaped for longer, which in a species with a lifespan, measured in decades rather than years, makes an enormous difference to how efficiently you can keep extracting calories from food well into adulthood. The diet flexibility angle is real too. Thicker enamel lets you fall back on tougher, grittier foods during scarcity. Not necessarily the hardest foods, but the abrasive ones that would grind thinner enamel down fast. Thick enamel shows up across multiple primate lineages that evolved it independently, which suggests the advantage is general durability rather than one specific dietary trick, and that evolution kept arriving at the same solution from different directions. Your teeth were built for a much longer, harder life than a bowl of overnight oats requires. They're just quietly prepared for the worst anyway. If you like this video and want to learn more about evolution, check out these other videos.